I'm going to speak about exploring the instance space analysis for the maximum flow problem. Thus, we'll speak about maximum flow problem as a case study about its importance and the gaps in the literature for that. And then we are going to discuss what's the instance space for that, how we can store more insights about it. So the results that I'm going to present today are mainly based on one of our massive paper, which is accepted for publishing in European Journal of Operational Research. And we are going to discuss some results as well in our second paper, which we have submitted to Computers and Operational Research under review, but the preprint available in SSRM. Our project is supported by three sources of funding: the Australian Research Council, the Optima, as well as the Melbourne Research Scholarship is supported my PhD project. And we use the high computing system of the university for doing massive computation. So that's about that. And so what's the maximum flow problem? So if you have a capacitive network, that is a network with limited capacity, and its arcs, the aim is to send the maximum possible flow from one node to another node, such that the flow don't exceed the capacities, and the inflow and the outflow in each node are the same. That is, we have no excess or deficit in that node. And by flow, I mean many kinds of flow, from the electricity flow, water flow, or it can be commodity, it can be people, livestock transportation, networks, data and information networks, and so on. So why maximum flow problem is important? So in network, in theory, we have two basic problems for the network flow problems. One of them is the shortest path problem, which models the length of the arcs. Another is the maximum flow problem, which we discussed it, and it models the capacity of the links. Thus, this together captures all elements of the networks. Thus, any network in the network flow theory can be stated as one or both of these, or combination of both of these problems. Therefore, maximum flow problem together with shortest path problem constructs the nucleus of the network flow theory. This is why it is important in theory. But in practice, so it has a variety of applications in different domains. For example, in network designs, we have many applications to testing the network reliability, network connectivity, and it has many applications in electrical networks, and so on. In computer vision, it has also some applications, such as depth detection, image segmentation, object detection, which is very important in autonomous vehicles nowadays. And some of the scheduling problems also can be modeled as a maximum flow problem. It has also some other applications, for example, in modeling the traffic congestion or to modeling the evacuation problem. So, because of the importance of this problem, that is the maximum flow problem, this problem has been studied for more than 6 decades, and many algorithms have been proposed for that. And designing new algorithm, more strong algorithm or more fast algorithm is an active area nowadays. So the algorithms that designs for maximum flow problem has been studied in theory by worst case analysis, which is supported by strong mathematical and theoretical proofs. But what's the issue with the worst case analysis? The issue is that One of the issues is that the algorithms perform much better in practice than the worst case. Thus, worst case analysis cannot be give us a good measure to assess the performance of the algorithm in their practice. Another issue is that we can find some scenarios in practice that is contradict the worst case analysis. For example, we have in some cases we have an algorithm with the worst case analysis is better than the other one, but in practice worse than the one. Okay, so it's different practice. And the last but not least, so worst case analysis is an asymptotic analysis. This means that it regards the rank of the performance when some parameters like the size of the problem rise down to infinity. Thus, it cannot be used for per instance analysis, which means that in practice, we cannot capture the behavior of algorithms by worst case analysis well. Thus, we need some kinds of practical analysis instead of worst case analysis. The main approaches for practical analysis for maximum flow is competitive analysis, which is based on the hours performance. That is, the researchers use a set of instances and study that which algorithm is outperform the other ones in average in most of the instances, and then they say that this algorithm is the winner. But this competitive analysis has three main issues. The first one is that it cannot give us a good insight about the strengths and weakness of the algorithms. For example, when we say that this algorithm is better than that algorithm in average in most instances, so the question is why this is the case? Why it is better? There's no clue to answer this question for competitive. And the competitive analysis cannot say that if the set of instances that we have are fair or not for our analysis. Is it comprehensive or not? So this doesn't answer that question. And the final question is the final issue is about the algorithm selection. So when we have an algorithm that outperforms the other ones in most of the instances, this doesn't guarantee that it can be preferable for all instances that we have. Okay, especially for the unseen one. So based on these issues, we need a more scientific analysis in versus of the competitive analysis. So this is the main gap in the literature for the maximum flow problem and we want to study. Especially, we are interested in answering these questions. We are interested to know what are the strengths and weaknesses of the algorithms and how they are related to the characteristics of the problem or in the best circumstances. And we want to know which characteristics of the problem are more relevant to the algorithm performance. Another question is that how an algorithm outperform the other ones in specific instances with specific characteristics. That is what's the reason for that outperformance. We also interested to know how comprehensive is the set of instances we have. So in the literature, people usually use a set. And when you ask them why this set, they say because in the literature they have used that. But the question is it fair enough? Is it comprehensive or not? Enough or not? So we want to answer this question. And we also interested in know that with a comprehensive set of instances that we have, is it unbiased or biased? It's very important to carefully select the instance. And finally, using these insights, if we will be able to get these insights, the last step is to how to use them to improve the current algorithms. So to answer these questions, we use the instance-based analysis methodology, which is developed by Case team. So instance space analysis is a visual and per instance analysis, which is based on no-freelance theorem and Rice's algorithm selection problem. So the no-freelance theorem says that it is unlikely that an algorithm outperforms all other algorithms in all possible instances. Okay, and Rice's framework, Rice's algorithm selection problem tries to predict the algorithm of performance of an algorithm based on the characteristics of the problem. So here is the framework for instance space analysis. The blue part is our contribution into this framework, which I'll discuss later. So this whole framework is an enhanced instance space analysis, but the dark part is instance space analysis. The part that squared by dashed lines is Rice's framework, algorithm selection. So if you have a set of instances and a set of measurable features, then we also we have a set of algorithms and a performance measure. Then we aim to predict or to find the best to predict the performance of that algorithms based on these features. So the instance space analysis is going beyond just this prediction, and it provides a space of all possible instances, which is known as instance space. And also it tries to show us what are the footprints, or that is the strengths and weakness, the strengths of the algorithms in practice. And it does that by a projection approach, that is, it projects the instances into a two-dimensional plane to visualize what's going on here. Where we can see that how diverse are the instances. We can see the locations that algorithms performs well or not. This projection also is done in a smart way, that is not just to reduce the dimension, but it does that in a way that we can see the trends of the features. That is, for what the real value of the features may be increased from one corner to other corner of the instance space. So why it is important? Because in this way we can interpret or get more insights about the behaviors of the algorithm. To apply this methodology in practice, we use a MicroDot toolkit, which is provided by Andres and Nilufar, and it requires a metadata, which is collection of instances, features, algorithms, and a performance measure. So the initial metadata that we have used here includes around 8,500 instances, which is generated from 16 benchmark generators. We also have some instances from a real-world application in computer vision. We have 14 features, where 4 of them are from the literature, and 10 are the now features addressed for the maximum flow problem. We also have used just the simple instances that can be calculated easier than solving the maximum flow problem, because if it takes more time, it is not fair for algorithm selection. But if you just care about the insights, you can use more complicated instances as well, which I will discuss at the end. We used 4 algorithms. 3 of them are push-label algorithms. HIPR, which is a high-level push-label algorithm. The PAR is partial augmented relabel algorithm. P2R is 2-level push-label algorithm, and we use a pseudo-flow algorithm. So the performance measure that we use here is CPU time, and we also define the goodness for our algorithms. So we say that an algorithm in an instance is good if its CPU time is no more than 5% of the base performance on that instance. We also use some fundamental operation counts for the algorithms to get more insights, which are argscans, pushes, relayables. I don't go through more details about them, but I just mentioned here that which kinds of performance measure we have used. So let me explain a little more about the features. So the 4 features we have used from the literature are the simple ones, which measures the number of nodes, the number of arcs, which is very important to get the size of the network. We use the average node degree, which is important to know that how arcs incident to nodes in average, and also the density, which is one of the important features of the network, and it is compare the number of arcs in the network over all possible arcs that we can have in that network. We also use the spread of the node degrees, which is new for maximum flow. It hasn't been used for analyzing the maximum flow in the literature. So we use the coefficient variation of the node degree. We use also the coefficient variation of capacities to know the spread of the capacities through the network. We also use the arcs that the percentage of arcs that are less than average capacity or greater than average capacity. The range of the arc capacities we think that is important too. We use the skewness of the capacities, so it is important to know that how capacities are spread is again another measure for as in the spreadness of this capacities. This one also is the skewness of the capacities per node. It's related to the one. This one is one of the important but one of the most controversial features. It is a combination of this skewed capacities and the density, and it can be interpreted as the capability of network in holding or carrying an amount of load. So if you want to discuss that one, you can discuss more later. The last ones are one of the most important features, which captures the potential excess of the network. So I'll describe them a little in the next slide. So if you have a network, each link arc has a capacity. At the beginning, each node has a 0 excesses, that you have no excess or no demands on it. The maximum flow that we studied here are starting by simple initialization, which means that it sends the maximum possible flow from the source is neighbor nodes. That is, it saturates all source adjacent nodes. Now, in this network, if we do that, we push all excesses, possible excesses through these arcs, then node 2 will have excesses equal 10, and node 3 will have excesses equal 20. In the next step, the maximum flow algorithm tries to push that excess toward the source through the link arcs, single arcs, or maybe partial pass or a complete pass. It depends on the policy of the algorithm. So it pushes the excesses until it reaches to the source, or there is no way to send it to the source, to the sink. So in that case, it has to push it back to the sink. Thus, excesses are one of the most challenging part of the networks for the maximum flow algorithm. So it is important to measure the excesses in the network. But before running the algorithm, we don't know what's the exact excesses that will be appear during the process of the algorithm. So, but we can measure the potential excesses. That is, suppose that all Rs can be used with their higher capacities, and we calculated what is the excesses, possible excesses that can be confronted in the network. So here, the red points have excesses and the green points have deficits. So the excesses are the most important part, not the deficits. So to capture this difficulty, we use these potential excesses in our features. For example, we can sum them and divide it by the average capacity to obtain a feature, or you can sum them and divide it by the average capacity, then divide them by the number of nodes to obtain an average potential excess per. So thus these two features captures this potential. So based on this discussion and the metadata that I introduced, we constructed the first instance space analysis for the maximum flow, as you can see in this slide. So what's the issue with this? You can see that there is the instance space is sparse. That means that we need many more instances to fill the gaps that we have here. So this part belongs to the tiny instances. We don't care about them. They are not worth to be generated. But the other parts here must become more dense. In the right panel, you can see the footprints that is predicted for the same instance space, but we don't discuss them because we are not happy with this instance. To generate more instances, we use this pattern distribution of the instances for each benchmark generator. For example, you can see here four benchmark generators with their distributions. The black points are the distribution of the targeted generator or family. The carrying points are the new instances. Based on that pattern, we generated 2,000 nodes in the instance space, and the green ones are the rest instances that we have in the instance space. So in this way, we generated around 17,000 new instances and added them to our metadata and reconstructed the instance space to obtain this one. So as you can see, the density is improved. We have more dense areas, and but we still have a big gap here. This hole here, which means that we need even more instances. But here we have another serious issue, which is, as you can see, for example, here, many instances are similar and they are all like each other. Okay, so thus before going to generate more instances, we need to handle this issue, because this issue can impact this instance space analysis and the distribution of instances. Thus, before going to generate more instances, we are going to remove this oversampling bias. But why oversampling is important? In the instance space context, it is important because it impacts the estimation of correlation among the features and between the features and the algorithm performance. Thus, it misleads the feature selection. So notice that when we have an initial set of features, some of them may be irrelevant or garbage. So in the instance space analysis, we select the most appropriate one. And if we have oversampling, it misleads the feature selection. It also impacts the estimation of variance of the features, which is important in dimensionality reduction. Thus, oversampling can mislead the dimensionality reduction. And finally, we change the density and purity of instances across the instance space, which misleads the machine learning classifiers that used to predict the footprints of the algorithms. So, just one point, these issues are not just tied to instance-based analysis, and we are going to discuss them later. To reduce the impact of the oversampling bias, we devised an instance selection algorithm which selects among a given set of instances a subset that is uniform but diverse enough. So how we do that? To do that, we define similar and dissimilar instances based on a similarity, based on a given similarity threshold epsilon. So we say that two benchmarks are similar if their Euclidean distance in their feature space are less than the similarity threshold. For example, in this figure, you can see that the blue points are similar based on that epsilon that we have here. Also, the middle blue point is similar to the red one based on this similarity. But they are dissimilar with the other points in the space that we have. So we also made an similarity assumption. It says that instances with similar features are likely to result in similar labels. So here, these two blue points are similar and they have the similar labels. So it is what we think that's correct. But we see that we have two similar instances here, the blue one and the red one, which have different labels. So what does this mean? This means that it varies from the similarity assumption. Why? Because it means that we don't count something about that instance. Maybe we forget some important features about that. So we show such instances, we count such instances that have the similar distance but dissimilar labels by Visa, which means the labels of these instances may not be explained by the current set of features. It gives us a criteria to the adequacy of the features. Now, based on this, we say that an instance A is redundant corresponding to a similar threshold. If you find another instance which is similar to it and have the same label as it. Otherwise, we say that that instance is critical. Thus, the main policy of the instance selection algorithm that we have here is to remove the redundant instances. For example, if you go back to that instance we had previously, so we can remove one of the blue point and keep the rest up. To determine the similarity threshold, we need a new uniformity threshold. That is how uniform the set or the critical set wants to be. What kinds of uniformity we want to achieve. For example, maybe we need a set with uniformity equals 0.5. Thus, we try different similarity thresholds. The ones that give us a critical set with a favorite uniformity, it is our similarity threshold. Using this algorithm, we selected less than 1/6 of all instances. That is, more than 5/6 of instances are redundant. So let's say that, let us see that what happens with this instance. So this is, in the left panel, you see the final instance space we created using the selected instances with that algorithm. So you can see it has an acceptable uniformity. In the right panel, I projected all instances in the same space, as you can see that there is much difference in the uniformity. So the left one is more uniform, the right one is less uniform visually. But sorry, we can measure it using the nearest neighborhood distances, which give us around 0.83 for the left panel, and the right one has a 0.36 uniformity. It's measured scale from 0 to 1. So it's a big difference. And we also have 6 selected instances here. So now we can say that these set of instances are less biased. So, and you can see that they are diverse enough. So we have no many big holes here. So the bottom of this part belongs to the tiny instances, which I said they are not useful. We don't care about them. The only part that can be filled is this one and this one somewhere. But because of the computational limitations and storage limitations, we believe that for future works. But we are happy with that instances. They are diverse enough. We have enough instances. So in the set of instances, we have done. We obtained a good set of instances. But what about the features? Let us say that discover if the features are also enough or not. What's their capability? So we measure that by the ratio of these dissimilar instances over the all critical instances. So in this way, so in this part, you can the black one are the visa instances that they are similar with some other instances, but they have different labels, which means that the Q clusters are not enough to capture that labels. But 63% of the other instances can be described well. Okay, so remember that when we define our features, we limited ourselves to just simple instances. We know that there are some important instances, but because of the computational limitation, we don't use that. Based on that limitation and this value, we can say that, yeah, the current features are enough to assess to obtain more insights about the algorithms and install space. So based on this, we are going to provide some more deep insights. So how do that? So in the top row, you can see the behavior of the algorithms. The blue points are the instances where each algorithm is labeled as good, and the orange one are the instances which is the algorithms are not good on them. In the top right panel, you see the good prediction for all algorithms in the portfolio. In the next 2 rows, you can see the trends of the features. So here the colors are scales from 0 to 1. The dark blue color means the lowest value of that feature, and the yellow light one means the highest value of that feature. So because features have different values, so we need to scale them to compare them. Now, look at the trends of the feature. For example, about the size. So in this part, we see the blue points means that the size of the networks are small here, and increase from this part to that part, which belongs to the huge networks or more than networks. Order is increasing from this part to this corner, and so on. So we use these trends to capture the footprints of the algorithms and to understand why they behave in this way. So one more important thing here is about this density. So density is one of the important features. As you remember in the previous one, so it hasn't selected as the member of the features, but we use it here. So density can be used easily with average node degree and order. So the reason that it hasn't selected is that because it can be calculated easily with these two ones, which means that we have a rich setup in features. So for that, we have here 60.63 for the capability of the features, but we see that they are rich enough to decide their performance. So let us describe a little more about this footprint. So as you can see in the top right panel here, so here in this part, in the bottom part, we have PAR and P2R, which takes that part. So what is specific about this part? So we can describe it based on this picture, which is related to the potential excess. We can see that the potential excess there is quite low, which means that the nodes have no much excess, which means that they are not challenging for the algorithms. Okay, so the algorithms, when push the excesses, they don't need to push it back because we have no excesses. We can be pushed through the source easily. We also, based on the density here, we can see that they are sparse or moderate instances. They have small or tiny density, which means they're too sparse or sparse. Thus, the networks in that part are sparse and they are not challenging for the algorithms. So what does this mean? This means that simple algorithms or moderate algorithms are more successful there than the heavy algorithms, which requires more calculation, which is the case about PAR and P2R. And why P2R is more successful than PAR here? So it's related to you can see about the node and the size of the one. So here in this part, the size of the networks increased, which makes the networks more challenging. And the P2R is a little from the PAR. It uses a trick for improving the PAR. This is why it is more successful in this area. But for that part, we even don't need that extra calculation. So in this way, you can explain all other features and see why they behave in this way. So I don't provide more discussion about this part. We also can check the hard instance. So for example, we can say that an instance is hard if less than half of the algorithms are good and so in this figure, for example, the instances with green or yellow colors are the easiest one, which means that more than half of the algorithms are good and so they are easy. But the blue ones are those that are hard, means that less than half of the algorithms are successful or are good and so we can obtain these insights in this way too. Now, that's enough for insights. We have discussed many insights about these tasks in this paper. I just list here the key achievements from our analysis. So we scrutinize the stability of the benchmarks that we have used. We explored the hard instances. We devised a statistical measure to capture the capability of the features. We visualized and understood the strengths and weakness of algorithms. We discovered why features may cause specific behaviors. And we revealed the efficient strategies in minimizing the fundamental operation counts. I haven't discussed that, but I provided a massive discussion in this paper. We also provided the method for automatic algorithm selection. So algorithms that used here use different policies from how to label the nodes, how to push the flows, and so on. One of the most important one is the uptime strategies, which we explore that it's responsible for the majority of the behaviors of the algorithms. We also specify potential areas for further improvements of the algorithm. So the last two bullet points, I'll discuss them a little more. So pathfinding strategies are the most promising areas for improving the algorithm performance. So this means that initialization is plays a crucial role in the performance of algorithm. Why? Because it's the base for algorithm performance for the pathfinding strategies. For example, again, look at the networks that we have previously. In the literature, the common initialization is simple initialization, meaning that they start by saturating all arcs adjacent to the source. It's also another saturating initialization, which is called saturating all arcs, which means that instead of starting with the simple one, what happens if we saturate all arcs? So why this is important? Because this allows us to explore the whole network with a low computational effort. So they are going to the literature. The saturating all hasn't been studied well. That's why we studied here a little more. And now initialization that we introduced here is saturating small arcs. So why we don't regard just the arcs with small capacities? That is, in this initialization, we just saturate or push flow from the arcs that has small capacities, for example, lower than average capacity. Okay, so the justification for this one is, again, at the same time that we explore many arcs with low effort, is that these small arcs are more vulnerable to saturating. That is, it may help us to saturate such arcs without extra effort. And the next one is saturating large arcs. That is, the saturating arcs that have capacities above average. It is again a similar justification with a little more. I don't go through the details, but if you are interested, we can discuss. So another thing is about global labeling heuristic, which is a heuristic used in push label algorithms to detect that which active nodes, that is the nodes that have excesses, which one can be reached to the sink or which one is disconnected. If it's disconnected, we can remove it from the rest of the process. So because the non-simple initialization, so here we have simple initialization and the rest of them are called non-simple initialization. With the non-simple initialization, when we saturate many arcs, many activate nodes may be disconnected from the source. That is better to remove them without more effort. So we apply this one for the push-label algorithms. So applying this initialization strategy together with the global relation heuristic give us 15 new algorithmic variants, which in total we have 19. So here we compare that initialization for each algorithm. So here, as you can see, one initialization for this IPR improved that algorithm greatly. It's competitive with the simple one. But in the rest of the algorithm, the simple initialization is the best one in majority of the instances, but also the saturating large arcs also improve the performance of algorithm in remarkable area. Okay. And another interesting thing is about the similarity of behaviors of this initialization in these three algorithms, which indicates that the impact of initialization is more relevant to the characteristics of the instances. But the policies, differences in policies also is impacted. So if for each algorithm, you want to detect which initialization is used, you can use this class, and the behavior and the reason for that footprints is also explained as previously done for the simple initialization. Now let us compare all initialization together, not just for each algorithm. So if you compare all them, we obtain this, the left panel, which again, the simple initializations of algorithm are more successful, but we have a new candidate here, which is this saturating last initialization for pseudoflow algorithm, which takes a remarkable area. And in the right panel, we have just the original algorithm, the simple initialization. One interesting thing is about this P2R. So if you replace HIPR, which is a weak algorithm in the right panel, with another strong algorithm, that is this new version of pseudoflow, we can see that the P2R algorithm shows more stable performance. Meaning that area can be recommended for P2R instead of sharing with PAR. So this means that if you have more algorithms, we can judge the performance of the algorithm better. So that's about the results. Now let us discuss the feature words and limitations. I just make it quick, I think, yeah. So about the instance, so what we have, what it is important to fill the holes in the instance space is to generate instances with specific characteristics. It's one of the most challenging tasks in experimental analysis, so it demands more work. Another things about the instance, so here we survey that they are hard, most of the instances are hard, but that hardness definition is based on the comparison between the algorithm labels. But also it is interesting to find instances that enforce algorithms to reach a higher level of complexity. For example, let's say that if the worst case complexity of algorithm is n squared, is there any instances to enforce that algorithm to reach that complexity or not? This is a good question. Also, collecting more real world instances are interesting. Here we just use computer vision for real world applications, but we need more applications or realistic applications to judge the practicality of the algorithm in practice. The benchmark generator that we have used here, they are designed more than 30 years ago, and they are designed mainly to challenge the push reliable algorithms and the previous kinds of algorithms, augmented path algorithms. Thus, they are not challenging enough for the new algorithms. Thus, we need to generate new benchmark generators which are generate challenging instances for the new algorithms. We assess the comprehensivity of the instances visually here, but it's better if you give us a measure for a statistical measure for that. For features, we use just simple ones, but as I said previously, you can use more complicated features. For example, weighted clustering coefficient, which is calculate how nodes are connected to their neighbors in one of the most important features in the retail, but it takes n power 4, which is much higher than n 1.5, which is the worst case for some maximum flow problem. But it is good to try these features to get more insights. For the algorithms, so we have the algorithms that we use here are general purpose one. It's good to include application specialized algorithms. For example, some algorithms are designed for computer visions, that works just on computer vision well, but not on the rest of them. And so parallel algorithms are also another options to study them for maximum flow. And about the initialization strategy that we have here, we observe that large saturated arcs are promising, give us good performance. If you can do that in a more smart way, it may improve the performance of algorithm better, or we can randomly saturate the many arcs together to see what happens. And finally, for the performance measure, the quality of the solution, memory usage, and so on can be included as well. And for my last part, I mentioned that the instance selection algorithm is not tied to instance-based analysis or to the maximum file. It is more general. Thus, if you are concerned about the correlation among the features, such as in feature selection, or you're concerned about the correlation between the features and the labels, which is the case for feature selection, regression analysis, classification, and so on, or you care about the variance of the features, dimensional reduction, or the density or similarity of the instance is important. So you have to reduce the sampling bias, and thus my algorithm can help you. The instance space that we have here can be explored online at Mattel.io website, and the source code that is written in C for benchmark generator, algorithms, extraction, so can be found in my GitHub repository. Okay, so that's it, and thank you. If you have any questions, I'll be happy to take them.